Now in the last lesson, we have looked at the homologous series of alkanes, or the family of alkanes. This lesson we're going to look at the family of alkenes. Alright, and same as before, we're going to focus on three things. We're going to look at the structure and bonding of alkenes, and then the physical properties, melting point, boiling point, viscosity, and so on, and the chemical properties, meaning the reactions that alkenes can undergo. So we have previously learned that alkenes contain the functional group, the carbon-carbon double bond. Alright, so as long as a compound contains a carbon-carbon double bond, we know that it belongs to the family of alkenes. Alright, so again, let us try to construct the first four members of the family of the members of the family of alkenes. Alright, for the when we have one carbon, actually there's no such alkene. Alright, can anyone immediately think of why? Now the reason being, alkenes has the feature carbon-carbon double bond. Alright, so the minimum number of carbons that need to exist in an alkene is 2. Alright, you cannot have a carbon-carbon double bond with only one carbon atom. Alright, so the smallest member, or the first member of the alkene family, contains 2 carbon atoms, and it has a carbon-carbon double bond. Alright, now bear in mind once again that carbon atom can form 4 bonds, no less, no more. Alright, and each carbon atom has already 2 bonds because it's a carbon-carbon double bond. Alright, so each carbon atom can only form 2 more bonds, and they are bonded to hydrogens. Okay, so the first member of the alkene family has 2 carbon atoms, and it has a molecular formula of C2H4. Okay, let's look at the next member where we have 3 carbon atoms. Now, even though we have 3 carbon atoms, the feature of alkenes is that there is 1 carbon-carbon double bond. Alright, so I can either put on the carbon atoms on the left or on the right, it doesn't really matter. Okay, so over here I've put the carbon-carbon double bond over here. Now I need to construct the entire molecule by filling in the missing bonds. Alright, for the carbons with the carbon-carbon double bond, the carbon on the left can form 2 more bonds. The carbon in the middle can form only 1 more. Okay, why only 1 more? If you take a look carefully, it has already formed 1, 2, and 3 bonds. Alright, so it can only form 1 more bond. As for the carbon atom on the extreme right, it can form 3 more bonds. Okay, so propene will have a structure that looks like this. Okay, and it has a molecular formula of C3H6. And lastly, we have butene. Butene has 4 carbon atoms. Okay, it has a carbon-carbon double bond. I can put it anywhere for now. Alright, so I put it between carbons 1 and 2 from the left. And then now I'm going to fill in the remaining bonds and the remaining hydrogens. So that will give me the structure of butene, which has a molecular formula of C4H8. Okay, like for alkanes, now I'm going to throw a difficult question at you. What happens when I have an alkene with 100 carbon atoms? For alkenes, it's going to be easier. If you inspect the molecular formulas, it should be obvious that the number of hydrogen atoms is 2 times that of the carbon atoms. Alright, so for an alkene with 100 carbon atoms, there will be 200 hydrogen atoms. Alright, that will also allow us to construct the general formula for alkenes to be CnH2n. Now the other important thing to take note about alkenes is this. Alright, so if we look at this carbon atom over here, alright, the one that I've just circled, now how many other atoms is it bonded to? Let's check. This carbon atom is bonded to 1, 2, 3 carbon atoms. Okay, what does it mean? Remember, carbon can have a maximum, can be bonded to a maximum of four other atoms. Alright, but this carbon atom that I've just highlighted is bonded to only three other atoms. What it means is that there is a possibility to add a fourth atom to this carbon. Alright, and how do we do so? Of course, we need to break one of the bonds here first. Okay, now the fact that we can add one more atom to each carbon atom in the carbon-carbon double bond, what does it mean is that it is coordinatively unsaturated. Okay, coordinatively unsaturated because it contains a carbon-carbon double bond which can be broken. Once it's broken, we can add more atoms to the alkene. So as mentioned, alkenes have the general formula CnH2n plus 2, alright, and it is unsaturated. It contains one or more carbon-carbon double bonds, and more atoms can be added to it. Right, once we break one of the carbon-carbon double bonds, then we can add more atoms to the carbons across the carbon-carbon double bond. Now, alkenes can exist as different isomers again. Alright, now it is slightly more complicated also. Now let's look at structure A, B, and C. Okay, in this case, all three structures have the same molecular formula. It's C4H8. Alright, but let's inspect if the structures are the same. Okay, if you want, you can take 1 minute. You can pause the video here and take 1 minute to inspect the three structures. Otherwise, I'm going to review the answer in a while. Okay, now all three structures are different this time round. A is not equals to B, is not equals to C. Alright, A and B look similar. Alright, but however, the position of your functional group is different. Okay, and once the position of the functional group is different, you can see that actually the carbon atoms, they actually have different neighbors. Okay, what do I mean by that? If you look at structure B, there are 2 carbon atoms that are bonded to 3 other hydrogen atoms, but in structure A, you only have 1 carbon atom that is bonded to 3 other hydrogen atoms. Alright, so A and B, they are different. Now, how do we distinguish between structure A and B? Alright, we have learned that an alkene with 4 carbon atoms is called butene. Alright, so structure A is actually called but1-ene. Structure B is actually called but2-ene. Alright, how do we get the number 1 and 2? Is this. This is again to name an organic compound, there is a set of arbitrary rules. That means a set of rules that are agreed upon by scientists. And once we learn these rules, we will know what a name represents. We will learn how to name a compound also. So what is the rule for naming the alkene in this case? Is that we will number the carbon atoms starting from the side that is nearest to the functional group. Okay, so in numbering butene, I will number this carbon as 1, 2, 3, and 4. Okay, instead of the other way around. Okay, because we will always start numbering from the side that is nearer to the functional group. Okay, so now your carbon-carbon double bond is across carbon 1 and 2. Alright, so therefore we use the smaller of the two number. We say we name the alkene but1-ene. Okay, let's look at structure B. Now structure B, there's no difference whether you start numbering from the left or on the right, because you end up with the same set of number 1, 2, 3, 4. Okay, so now your carbon-carbon double bond is across carbon 2 and carbon 3. Again, we pick the smaller of the two number, we call it but2-ene. Alright, so when we see the name but1-ene, it should occur to you that there's a carbon-carbon double bond between carbon 1 and carbon 2. Okay, and when we see but2-ene, it should occur to you that there is a carbon-carbon double bond across carbon 2 and carbon 3 in the structure. Okay, now structure C is totally different from A and B. This is similar to the one that we saw for alkanes. And in order to name this compound, again the keyword is the longest continuous chain. Okay, it's more complicated now with an alkene, because your longest continuous chain must contain, okay, your functional group. Okay, so you must try to get the longest continuous chain that contains your functional group. So in this case, this is one of them. Alright, or if you want this, no, wrong, this is another one. Alright, okay, so first we name the longest continuous chain. If we look at the longest continuous chain, there are 3 carbon atoms, so we call it propene. Okay, and after naming the longest continuous chain, there's still a branch. Remember, there's still a branch that needs to be named, and the branch contains only 1 carbon atom, so we call it methylpropene. Okay, now if you come across if some of you may be wondering what happens when we have a more complicated alkene, how are we going to name that? Don't worry. Alright, the rules for naming is not really in syllabus. When you go up to higher levels, you will learn more and more rules for naming organic compounds. If really required, in the question they will give you the names of a few compounds, and from there you can deduce the rule. Alright, you will have to try to determine what is the rule that's shown in the pattern displayed in the examples given in the question. Okay, otherwise the rules that we have gone through in this lesson would be sufficient for you to name the compound in any question. Now that we have looked at structure and bonding, we're going to move on to physical properties. The good news is that alkenes have the exact same physical properties as alkanes. Okay, so they have low melting point, boiling point. The melting point, boiling point increases as the size of your alkene increases. Okay, they are insoluble in water, they are soluble in organic solvents. The viscosity will increase as the size of your alkene increase, and the flammability, meaning it's harder to catch fire as the size of your alkene increases. Now we'll move on to the chemical properties of alkenes, meaning the type of reactions that alkenes can undergo. Alright, before we look at the distinct reaction that alkenes can undergo, I just want to point out that any organic compound, alright, be it alkane, alkene, alcohol, carboxylic acids, any organic compound can undergo combustion. Alright, so even though we don't mention combustion in alkenes, alcohols, carboxylic acids, they can undergo combustion as well. And the same rules apply. Complete combustion would produce carbon dioxide and water. Incomplete combustion will produce carbon monoxide and water. Now, so as mentioned, alkenes can undergo combustion even though it's not explicitly stated here. Alright, and the thing about combustion of alkenes is this. Alright, combustion of alkenes, it will produce a sootier flame. Okay, sootier flame than alkenes. Okay, what do I mean by sootier flame? Meaning in the flame you will see more black soot than when you are burning alkenes. Now, why is that so? Now, if you compare the molecular formula, alright, of let's say ethene and ethane, okay, you will find that alkenes have a higher percentage of carbon in the compound as compared to the alkane with the same number of carbon atoms. So what happens when you have a higher percentage of carbon is that it's harder for it to burn completely, which means there is a greater extent of incomplete combustion leading to the production of carbon monoxide and also carbon in the form of soot. Alright, so when you are burning alkenes and alkanes, one way to distinguish them, or if you see a very sooty flame, it means that it contains your carbon-carbon double bonds, or it contains many carbon-carbon double bonds. Alright, now other than combustion, the more important reaction that alkenes can undergo is based on the fact that it is unsaturated. Now, as mentioned, unsaturated, if you look at any alkene, the carbon at the functional group, the carbons in the functional group, they all have only 3 neighboring atoms. That means they are bonded to only 3 atoms, meaning we can add a 4th one to each carbon atom in the functional group. Okay, but before we can do that, we have to break a bond. Why? Because the carbon atoms, they already have 4 bonds. Alright, so we cannot add any more bonds to it. But once we break one of the bonds in the carbon-carbon double bond, alright, then we can add more atoms to it. Alright, so this kind of reaction, we call it addition reaction. Alright, what is happening is this. In an addition reaction, first thing that will happen is that one of your double bond, one of the bonds in your double bond is broken, and the bonds in your reactant is broken. Okay, so I'm going to try to erase it. Okay, and once the one of the bond in the the carbon-carbon double bond is broken, now each carbon atom can form one more bond. Alright, so it will add atom X to one carbon and atom Y to the other carbon. Alright, so essentially the alkene will combine with another substance, and because you are simply adding to it, you only have one new product, okay, which is called the addition product. Alright, so alkenes undergo addition reactions because it is unsaturated. Now, what things can we add to an alkene? We can add 4 things. We can either add hydrogen, we can add halogen, alright, meaning chlorine or bromine, we can add water, we can add another alkene. Alright, so now we'll look at 2 things. First thing is that each kind of reaction, each thing that we add to an alkene, there's a name given to it. Alright, the name of the reaction. First thing, and then secondly, we'll try to predict what is the product that is formed. Alright, now when we add hydrogen to an alkene, alright, the reaction is called hydrogenation. Okay, hydrogenation. So what is the product that is formed when we add hydrogen to an alkene? Let's see. Alright, so we start with an alkene, which is this. I have not filled in the rest of the atoms. So in order to get the product, we need to erase one of the double bond first. Okay, that will allow us to add two more bonds. And what are we adding to the alkene? We are adding hydrogen and hydrogen. Okay, let's imagine that if we have hydrogens to start with, so the product that we get when we add hydrogen to an alkene is that we will get an alkane. Okay, next, when we add halogens to an alkene, the name is called halogenation. Okay, if we are adding bromine, it's called bromination. If we add chlorine, it's called chlorination. Alright, now the addition of bromine to alkene is more significant, as we will see later. Alright, so what happens when we add chlorine to an alkene? Let's see. I'm going to apply the same steps again. I'll draw out my alkene. This is my ethene. I will erase one of the bond in the carbon-carbon double bond. Alright, I'll erase one of the bond in the carbon-carbon double bond. That will allow me to form two more bonds, one each for the carbon in the functional group. Alright, so now I'll add bromine and bromine. Alright, so this is your addition product. Now how do I name this compound? I call it, since the since the alkane contains bromine, we call it bromoethane. Alright, and since there are two bromines, we call it dibromoethane. Alright, now for this particular product, we further need to add a 1,2-dibromoethane. Why 1,2? Is to tell you that the bromines are added to different carbon atoms. Okay, so there's one bromine on carbon number 1, there's one bromine on carbon number 2. Alright, why is that important? Is when you're adding something to an alkene, alright, each carbon atom in the functional group will form a bond to a new atom. Alright, so if you add bromine, the two bromine atoms will be added to the two carbon atoms that are side by side. Alright, so it won't be a case where you have both bromine atoms going to only one carbon atom. Alright, so the atoms that are added to an alkene will always be added to the carbons that are side by side in the functional group. Alright, the third thing that we can add to an alkene is called water, and my favorite part about this is usually I'll get students to name the reaction, and the common answer that I'll get is wateronation. Alright, again, thankfully scientists have taste, scientists have class. We don't call it wateronation, we call it hydration. Okay, hydration means the adding of water to an alkene. Alright, so what do we get when we add water to an alkene? It's this. Okay, so water can be represented like that, H2O, so H and OH. Alright, so first thing, I need to break the double bond in the alkene. Next, I need to also break the bond between H and OH. Alright, then I'll add H to one carbon and OH to the other carbon. Now what is the product that I get? Okay, may not be very clear here. Let me try to draw again. So I will add a H and a OH. Now if you take a look at the product that is formed, what is this product? It is actually an alcohol. How do I know it's an alcohol? Because there is this feature, your OH functional group. Alright, so the product of hydration of alkenes is alcohols. Okay, the last thing that we can add to an alkene is another alkene. Alright, so how do we add an alkene to another alkene? This one I will leave it to the last part to show you. Okay, so what is going to happen next is that we're going to look at each reaction in greater detail. So greater detail meaning the reagent conditions, alright, and the exact products that we're going to get. We're going to recap for that. The first reaction that we look at is hydrogenation, meaning the adding of hydrogen. Now the conditions you need to remember is 200 degrees Celsius, and you need nickel catalyst. Alright, so the products we have already seen. If you start with ethene plus hydrogen, what we are going to end up with is your ethane. Okay, so any alkene undergoing hydrogenation, you will get the corresponding alkane. Corresponding meaning the alkane with the same number of carbon atoms. Okay, next we are going to look at halogenation, or in particular bromination. So the conditions for this reaction is room conditions. Room conditions meaning you don't need any special condition. That means if you were to perform it under room conditions, the reaction will take place. Okay, let's take a look at the product first. So once again, if I have ethene reacting with bromine, the product that I will get is by breaking the double bond, one of the double bond, and adding a bromine to each carbon atom. Alright, this is your 1,2 dibromoethane. Alright, now what is so special about this reaction is that you will see, you will make some very obvious observations if the reaction takes place. Why? If you can recall, in periodic table, in the chapter of periodic table, we learned halogens. We learned that halogens are colored. Alright, so bromine is actually reddish brown. Okay, when bromine undergoes addition to an alkene, the bromine will disappear. Alright, so there will be an obvious color change from reddish brown to colorless. Okay, for those of you who are interested, please go to YouTube and search for bromination of or bromine to alkenes, and you will see the decolorization. Okay, we call it decolorization of bromine from reddish brown to colorless when it reacts with an alkene. Alright, now another reason why this reaction is very important is this. Alright, reaction with halogens, we have seen it before. Alright, we have seen that alkanes can also react with halogens. Okay, for example, if I have ethane, alright, and I mix ethane with bromine, now there is a possible reaction as well. Okay, what kind of reaction? We have learned that it can undergo substitution. Alright, so one of the hydrogen can be substituted with the bromine. Okay, but the key thing to remember about substitution reaction is this, that it requires a special condition, which is UV light. Alright, so addition of bromine becomes very important to distinguish whether the compound that we have is an alkane or is an alkene, or whether the organic compound that we have contains any carbon-carbon double bond. Why? If we add bromine to an alkane under room conditions, the bromine will remain, so the reddish brown color will remain. If we add bromine to an organic compound, to an alkene or an organic compound that contains a carbon-carbon double bond, the bromine will undergo reaction under room conditions, and then we will see a decolorization of the solution from reddish brown to colorless. Okay, so addition of bromine, as we will see later, can be used to distinguish between alkenes and alkanes. For alkenes, there will be a color change from reddish brown to colorless. For alkanes, there will be no color change, so the solution will remain reddish brown. Now the next reaction is hydration. So hydration, we are adding water to an alkene. Alright, we have seen that when we add water to an alkene, or when we add water to ethene, the product that we get is ethanol. Okay, it's an alcohol. Alright, this reaction requires special conditions also, 300 degrees Celsius, 60 atmosphere, and we need a catalyst. This is called phosphoric 5 acid. Okay, phosphoric 5 acid as a catalyst to speed up the reaction. Now if you take note of the temperature and the pressure, 300 degrees Celsius, 60 atmosphere, as a student, how I remember it as 360 degrees, which is the angle for a complete circle. Alright, so 360. Alright, the other thing is this, 300 degrees Celsius. If you are adding water, are you really adding water? Answer is no, you are adding steam. Alright, so when stating the reagent for hydration, alright, do not put water, but you need to recognize that it is in gaseous form and put down as steam or H2O bracket G. Alright, so remember the reagent for hydration is not water but steam, and then the conditions will be 300 degrees Celsius, 60 atm, phosphoric 5 acid as a catalyst. Now the last reaction that we'll look at is the addition of alkenes to another alkene, and this reaction is given the name addition polymerization. Now why addition? Again, because only a single product is formed. Alright, and then what is polymerization? Polymerization is the opposite of cracking. Cracking is when you have a large molecule being broken down into smaller ones, but polymerization is the opposite. You have for example, a small alkene or many small alkenes combining, alright, combining to form a large molecule. Okay, so this large molecule is given the name as a polymer. Okay, the small alkenes that make up the polymer is called a monomer, and this process where monomers combine to form a polymer is called polymerization. Okay, we are going to learn this further when we look at a chapter called macromolecules, but for now these are some of the basic terms that are required. Alright, so over here the conditions for addition polymerization is high temperature, pressure and catalyst. There's no need to be specific because depending on the alkene, the temperature, pressure and catalyst will vary. Alright, so there's really no need to remember any specific numbers. Alright, but what do we get when we combine alkenes together? Let's see. Okay, for addition reactions, remember the first thing that must happen is that one of the double bond must be broken. Okay, one of the double bond must be broken. After breaking the double bonds, each carbon atom will now be capable of forming one more bond. Forming bond to what? It will form bonds to each other. Okay, so this representation is only part, is not the whole. All right, and what happens when each carbon atom bonds to the one beside it is that you will get one continuous chain of carbon atoms with no more carbon-carbon double bond in it. Alright, so essentially the addition polymerization, when you add alkenes to another alkene, the product that you get is a giant alkane. Okay. Alright, so it extends indefinitely to the right, it extends indefinitely to the left. Okay, so addition polymerization of alkenes will produce a long chain alkane. In the chapter of macromolecules, we're going to learn more about polymerization. We're going to learn more about how to represent polymers accurately.